Hey, this is 4.4 day one. So in 4.3, you learned about some properties of logarithms, like stuff that you can do with them to manipulate them. And we're going to use a little bit of that and also just finding similar bases to solve exponential equations. So in this first section right here, it says that you can rewrite the equation in the form um, b to the power of m equals b to the power of n. And then you can set these two things equal to each other like that and solve for the variable. So in these first two examples, I guess what my suggestion would be is if you see a variable in the exponent, you kind of have two ways that you can solve this. So one way that we've talked about is that 2 would be the b base bottom. So you could rewrite it as log base 2. And then the other two things flip sides. So you would have 16 equals 3x minus 8. And then you could do the change of base formula on this side. So you would do log 16 divided by log 2. And you would get 4. And that equals 3x minus 8. And then you could go ahead and solve. Sorry, this is not the best pen. And we would get x is 4. Now, the other option, and this is the way that they're wanting us to practice in this lesson, is to basically make this have the same base. So my tip-off would be use this number, and then in a calculator, like let's go to Desmos, we can do 2 times 2 times 2 a bunch until we get 16. So I guess what I'm saying is here, we want to rewrite this as 2 to some power equals 2 to the power of 3x minus 8. So what I would do here is just go 2 times 2, that's 4. Okay, keep going. Times 2 is 8. Times 2, that's when we finally hit 16, and we had to do it 4 times. So we would put a 4 up here because it took 4 tries. Then what step 2 is saying, we have the same base now. What step 2 is saying is to set the two exponents equal to each other. So we would go 3x minus 8 equals 4, and then again, drop your line and solve, which is the same thing we did on the other side. You would get 3x equals 12, and then x equals 4. So if we stick to just that new method in this other one, what we would want to do is try to get this to be a base of 5. So we'll do 5 times itself a bunch until we get 125. So twice, 3 times. Okay, 3 times does it. So what we can do is rewrite 125 as 5 to the power of 3. And then we have 5 to the power of 3x minus 6. So notice these match, which means that these must match. That's why we can set those equal to each other. So we would go ahead and say, all right, 3x minus 6 equals 3. Drop your line and solve. So you would get 3x equals 9, and then x equals 3. Okay, so that's your first option, or like the first thing we'll cover is just rewriting numbers so that the bases match, and then set the powers equal to each other. This next section is using logarithms to solve exponential equations. So inverses are I know we've talked about this before, but inverses are things that kind of like undo each other or make stuff go away. Doing the log doesn't make stuff go away, but it allows us some additional moves. So they're not inverses of stuff, but it lets us mess around with the equation a little bit more. So once you do the log of both sides, then you can use those properties of logarithms that you learned in 4.3 to manipulate it a little bit. So here in this first example, we have 4 to the power of x equals 15. Now, again, we have some tools. We learned to rewrite this in the last, like 4.2, I think it was. So we could rewrite this as log, and our b base bottom is 4. And then we flip the x and the 15. So we have 15 equals x. And now you could do the change of base formula and do log 15 divided by log 4 and get your answer. Okay? But this is just an alternative option. We're going to use what's called the power property from 4.3. So another strategy is for us to take the log of both sides. And what's going to happen is we get, all right, I'll just write it out. Log of 4 to the power of x equals log of 15. Seems like we're just making a mess, right? But what we know that we can do, because of our last lesson, is we can take that and we can move it out front. So we can go, sorry, changing color here is not very efficient. We can take that and go, pew, there. So then we have an x out front, and we have log of 4 equals log of 15. And we can divide by log 4, divide by log 4. Shoop. And then we get x equals log of 15 divided by log of 4, which is literally what we did here much more quickly, but sometimes you kind of need additional tools. So it's just another tool to throw into your toolbox. When you type that into your calculator, if we round it to 3 decimal places, we should get 1.953. Okay, if you want to pause the video, you can try this one. It's going to be the same process, but pause the video and use one method or the other to solve it. Okay, so if we use the new method to solve it, what we would have is we would go log of one side equals log of the other side. And we'll put 5 to the power of x here and 134 here. Then what we can do is take this guy, shoop, and bring it out, boop, and we get x times the log of 5x. Nope, sorry, the log of 5 equals log of 134. Then we can bloop, drop our line and divide by log 5 on both sides. When you type that in, you end up with, if you round to the 3 decimal places, you get 3.043. All right. On the next page, we have a couple other things, and these are some of the items that are highlighted right here. I'm just going through a few different examples. So, boop, 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 boop. Here we go. Okay, so on the second page, we have e to the power of x equals 17. And what's nice is when we have base e, we actually do have an inverse that kind of knocks it out right away for us. If we natural log both sides, we get natural log of one side, natural log of the other. So we have e to the x and 17. Natural log and e, they cancel each other out, so we end up actually just having natural log of 17. So if you see, whoa, that went crazy, sorry. If you see this, what's really nice is you can just natural log it, and it's your answer, natural log 17. There's nothing crazy that you have to do there. And then when you type that in, you get 2.833. Okay, I don't know why this is zooming challengingly. So number 6 is a little wild looking because there's some extra pieces to it, but basically all we need to do is get the e part by itself. So if we go plus 3 first, let me rewind. We're trying to find x, so we need to get it by itself. Let's peel away the easy stuff first. So if we do plus 3 on both sides, then what's left here is 40e to the 0.6x equals 240. Then if we divide by 40, we have e to the 0.6x equals 6. And now we have that natural log like we were just looking at previously. Once we have the natural log, once we have the e, we can natural log both sides, just like that last one. The e drops off, so then all that's left is 0.6. Give myself a little space. 0.6x equals the natural log of 6. I don't want to look at a decimal, so I'm just going to leave it as natural log 6 for the rest of this calculation. X is almost by itself, but we have this decimal, so we just divide by 0.6. So then what you type into your calculator is natural log of 6 divided by 0.6. So we'll go natural log of 6 divided by 0.6. Whoopsie. And we get 2.986 if we round to the nearest thousandth. All right. We have one left. This is a wild one. You guys are going to love it. And by that, I mean you're going to hate it. It's actually not terrible, but it just looks really, really, really intimidating. So I'm going to do a different example just to, I guess, hopefully help. If we had x squared minus 8x plus 7 equals 0, what we would do here is we would do this guy, where it multiplies to 7 and it adds to negative 8. If you want to pause the video to figure those numbers out, do it. Pause the video. Okay, the two numbers that multiply to 7 and add to negative 8 are negative 1 and negative 7. So in a previous section, what we would have done is we would have said x minus 1 times x minus 7 equals 0. Now, notice, this is the big thing I want to make sure you notice. We went from a power of 2 to half as much because those are technically powers of 1. So we split that guy up into like half and half on each one. And then here we add a single power of x, and it's still just like a single power of x, like if you want to compare those. But the big thing is these highlighted pieces. Then what we would do is we would go, okay, x minus 1 equals 0, and or x minus 7 equals 0. And we'd solve it like that, okay? It is the same thing, except here we have e to the x, so we're going to finish it up a little differently. So what we're going to do is we're going to say, instead of x minus 1, we're going to say e to the x minus 1. And then we're going to do e to the x minus 7. That equals 0. Okay, so take a moment. This thing got cut in half, same base, but half the power. Just like here, this thing got cut in half, same base, but half the power. Okay? Then we finish it by going e to the x minus 1 equals 0 and or e to the x minus 7 equals 0. If we add 1 to both sides, we get e, ooh, that's a bad color. We get e to the x equals 1. And then remember, we can natural log both sides. And when we do that, natural log, we get x equals the natural log of 1, which is 0 when you type it in. Over here, we do the same thing. add 7 to both sides, we get e to the x equals 7. Then we natural log, and we get x equals natural log 7, which is 1.946.